Meta-analysis in research methodology. Imagine you're faced with 10 high-quality research studies, all investigating whether machine learning improves student performance in online education. Each study uses a different dataset, method, or algorithm. Some show strong improvements, others show only slight benefits, and a few report no effect at all. You want to know, what's the overall impact? Is the effect real or random? Are certain model types more successful than others? Reading summaries won't help. You need a structured, statistical method to combine these studies and uncover the bigger truth. That method is meta-analysis, a rigorous quantitative technique at the heart of modern research synthesis. What is meta-analysis? Meta-analysis is a statistical methodology used to systematically combine and analyze the results from multiple independent studies that examine the same or similar research questions. Instead of treating each study as an isolated piece of evidence, meta-analysis integrates them to calculate a pooled effect size, a single value that reflects the overall strength and direction of an effect across studies. This increases statistical power, improves precision, and helps identify patterns that individual studies may not reveal. At its core, meta-analysis is not just a review, it's a form of quantitative data aggregation. It goes beyond descriptive summaries by reanalyzing the numerical outcomes of research, making it one of the most scientifically rigorous forms of secondary analysis. Key components and steps in meta-analysis. Formulating a focused research question. Every meta-analysis starts with a well-defined question, often structured using frameworks like PICO, population, intervention, comparison, outcome, or variations depending on the discipline. The clarity of this question ensures that all included studies are conceptually aligned. You can watch above video to learn how to create a PICO question. Systematic literature search. Researchers do a wide and careful search across online research databases like Scopus, Web of Science, or Google Scholar to find all the studies related to their topic. This is called a systematic search. They follow clear rules so that anyone else could repeat the same steps and find the same studies. This helps keep the process honest and reduces the chance of only including studies that show strong or positive results. This is called publication bias. To decide which studies to include, they use inclusion and exclusion criteria. These are like filters. For example, they only include studies that have real data from experiments or observations, not opinion pieces, editorials, or summaries. Measure outcomes in a way that can be compared across studies, like test scores, accuracy rates, etc. Provide the numbers needed for analysis, such as the average results, means, how spread out the results are, standard deviations, and how many people or items were in the study, sample sizes. This step makes sure all the studies in the meta-analysis are high quality and can be analyzed together. Study screening and selection. Using different tools, researchers screen studies by title, abstract, and full text. Inclusion decisions are based on relevance, methodological rigor, and availability of statistical results. This is where inter-rater agreement and Prisma flowcharts come into play to document how studies were filtered. Watch above video to learn how to use different tools to create a Prisma flowchart. Data extraction, collecting data from each study. After choosing which studies to include in the meta-analysis, the next step is to collect important numbers from each one. This is called data extraction. The information you need includes effect size. This tells how strong or big the result was in a study. There are different types, Cohen's d or Hedges g, used when comparing averages between two groups, like before and after results. Odds ratio or risk ratio, used when the outcome is either yes or no, like success or failure. Correlation, are used when you're measuring how two things move together. For example, more study time equals better grades. Sample size, the number of people or items in each group of the study. Standard deviation or standard error. These numbers show how spread out the data is. This helps measure how accurate the results are. Moderating variables. These are extra details that may change the results slightly. For example, if one study used a small dataset and another used a large one, that might affect how strong the results are. All of this information is usually written into a table, using software like Excel or Google Sheets. This makes it easy to organize and later analyze. Choosing the right effect size, picking the right measurement. Effect size helps you compare results across studies, even if the studies use different scales or methods. Here's how to know which effect size to use. Cohen's d, Use when you are comparing the average scores of two groups, like test scores of students who use two different learning methods. Odds ratio or risk ratio. Use when the outcome is something that happens or doesn't, like whether or not a system crashed. Correlation are used when you're checking the relationship between two things, like more training hours equals higher model accuracy. Hedges G, very similar to Cohen's D, but better when the studies used small sample sizes, less people or data points. This step helps ensure that all results can be compared fairly, even if the original studies were different. Statistical modeling, putting the numbers together. Now that you've got the effect sizes, you need a method to combine them. There are two common ways to do this. Fixed effect model. This assumes all studies are measuring the same thing and that any differences in results are just due to random chance. Random effects model. This assumes the studies are a little different from each other, for example, different populations, tools, or methods, so it allows for real differences in the results. Most of the time, researchers use the random effects model, especially when the studies are not exactly the same. Assessing heterogeneity, checking for differences between studies. Sometimes the studies in a meta-analysis give very different results. This is called heterogeneity, and it's important to measure it. Here's how we do that. Q statistic, a test that checks whether the differences between the studies are more than just random noise. I superscript 2 statistic, shows what % of the differences between the studies are real. For example, if I superscript 2 equals 75%, that means 75% of the variation is due to actual differences between studies. Tau superscript 2, a number that estimates how much the true effects vary across studies. If there's a lot of heterogeneity, it means we may need to look deeper. Maybe some studies worked better because they used different methods or settings. Publication bias analysis, checking if some studies are missing. Sometimes, studies that show positive results are more likely to get published. This is called publication bias, and it can affect your final results. To check for bias, researchers use funnel plots, a type of graph that shows whether the studies are balanced or missing. If it looks uneven, some results might be missing. Egger's test, a mathematical test to see if the funnel plot is skewed or not balanced. Trim and fill, a method that estimates what the effect size would look like if the missing studies were included. This step makes sure your results are not being unfairly influenced by only looking at published successful studies. Subgroup analysis and meta-regression, digging deeper. If the results across studies are very different, we can do extra analysis to find out why. Subgroup analysis. You divide the studies into smaller groups based on some feature, like which type of algorithm they used or which year the study was done, and then compare the results. Meta-regression. This is like regular regression analysis. It helps you see whether a continuous variable, like dataset size or training hours, changes the strength of the results. This helps you find patterns and figure out what factors may be influencing the results. Visualizing and understanding the results. After all the analysis, it's important to make your findings clear and easy to understand. Researchers use graphs like forest plots, a chart that shows the results from each study and the combined overall result. It also shows confidence intervals, the range where the true result probably lies. Funnel plots helps check if studies are missing or results are biased. Bubble plots, used in meta-regression to show relationships between different factors. Finally, when interpreting the results, you don't just look at whether the overall effect is statistically significant. You also think about how big the effect is, how confident you are in the result, and how consistent it is across different conditions. I hope you now have a clear and simple overview of what meta-analysis is and how it works. If you found this helpful, don't forget to subscribe to the channel for more easy research guides.